Okay, so see, we have gone through a lot of math to explain the behavior we saw in our first attempt to discretize a differential equation, right? And this kind of analysis is going to be quite useful, not just for this particular case, but as we go a little bit more complex in our like tour of differential equations. So remember, we have started by simplifying this differential equation, du dt plus a times du dx is equal to kappa times d square u dx square, right? And we said, let's say kappa equal to 0 to start with. And let's now take our view a little bit further to include the case where kappa is not exactly equal to 0. And let's start by looking at the case when kappa is actually pretty small, right? So let's actually again look at the demo, and let's set conv diff. Let's still set our a to be 1 so that the solution should move towards the right, at a speed of 1. Now let's set our kappa to be something small, let's say 0.01. Actually, let me give it another one. So basically, when kappa is small, our solution should actually be pretty similar to what we have before, to when u is equal to 1, kappa is equal to 0, right? Because I'm adding really a tiny term. So basically, the purpose is so that you can still see roughly the behavior before and see how this addition of a small second order derivative is going to change the behavior of the solution. And I'd like some of you to come up and draw another initial condition so that we can observe what is the effect of a small second order derivative term. All right, please. Yeah, thanks. Looks like the kappa is 0.00, but yeah, actually 0.001. Gosh. All right, thank you. So we can see that the solution still behaves like before, right? It moves towards the right without changing shape much. But can somebody spot what's the difference between this case and what we have observed before?
Is the amplitude decreasing?
Yeah, the amplitude seems decreasing, right? Although very not much noticeable. It's smoothing out, right? You can see like the solution now, it actually appears much smoother than when you first drew it. So amplitude decreasing, becoming smoother. All right. And now let's actually start to look at, just to confirm this effect by looking at a slightly bigger kappa. So let's actually increase kappa by a factor of 10. See, you're kind of dozing off. Can you come and draw initial condition that kind of helps you wake up a bit? Sorry. Yeah. Cool. Thanks. And now we can see that the valley drawn seems to be kind of just shrinking, right? I mean, magnitude pretty fast, and the solution becomes smoother and smoother and smoother very fast. Okay, and to kind of get the extreme of this, let's actually set how about I have no speed. Right. Well, if I have no speed and no kappa, it's basically it's moot. I mean, anything I draw is gonna stay like that. I mean, not interesting, but like if I have 0 u and actually I set kappa equal to 1, right, which is strong. Can somebody draw a solution and tell me, I mean, before you draw the solution, can somebody tell me what the solution look like? What do you think the solution look like? Just do that. Okay, can you come and try and see what can draw something that does that? And please observe how different features are going to change in different speeds. Seems everything just erases out, right? Get the features got like disappear pretty soon. But did somebody notice like the very sharp teeth actually disappears first, and the larger scale features like this part was higher than this part on average actually get disappeared a lot slower. See that? Right, so if I do that again with a smaller right, you see that, like the teeth, let me actually do that even slower. Right, this part gets smoothed out really fast, and then the larger scale features got smoothed out over time, less quickly. Eventually everything becomes flat, right, as you saw before. So this is the effect of the second order derivative. Okay, actually the equation I just simulated with a zero velocity and a non-zero kappa, a non-zero second order derivative. It's sometimes called a heat equation. Why is that the case? Because the equation actually describes how a non-uniform temperature distribution evolves in time. Okay, so if you have, let's say, a uniform steel bar, and you have non-uniform distribution of temperature, so somewhere is hotter, somewhere is cooler, and this is how the temperature eventually becomes uniform over time through conduction, right? And if you write down the equation for conduction, you get exactly this guy without the A.